Okay, we're going to start. The interface looks a little different today because that's pretty much all I can get to work today. I hope folks on Zoom can see the screen share. Yes? Okay, thank you. All right. Announcements to begin. A reminder about homework 2 that's due on Feb 18th. Homework 2 covers linear models. There are a couple of theory questions around mistake-bound learning, including a proof of the perceptron, a variant of perceptron really. And there's some experiments where you implement several different kinds of perceptron type algorithms. The usual advice is start soon if you haven't already. This could take time. Also, the theory questions are easier than they look. No, seriously. They look heavier than they actually are, but if you think about it, you'll find that the answer is actually rather simple for both the theory questions. Please use Piazza for discussion, come to office hours if you haven't already, and start soon. Any questions about homework 2? Have people started? Some people. Okay, and some people are laughing nervously. Start soon. And for project, I don't have updates yet. We're still trying to finalize the data set that you'll be working on. Sometime next week, you're going to get more details. Okay, any other questions or concerns you want to discuss? If there's nothing, we're going to go into the content of today's lecture, which is least mean square regression. This is a new unit. We are still talking about linear models, but we're talking about regression with linear models rather than classification. Quick show of hands, how many people have seen linear regression before? Many of you. And how many of you have seen linear regression with stochastic gradient descent? Smaller set. The point of this lecture is to kind of make sure that all of you are on the same page with respect to these topics. And there's another goal here, which is we will, you'll be looking at a certain way to think about learning that shows up here, and that actually is the primary way in which we've designed learning algorithms for the most part. That's the idea of framing learning as an optimization problem. So let's get started. We'll start with the least mean square with examples of least mean square regression, then talk about this objective function that we would like to optimize for training this regressor. And then we'll talk about two different strategies for solving this optimization problem, namely gradient descent and stochastic, or sometimes in the earlier literature, it was also called incremental gradient descent. Let's start with some examples. This is a sort of a dummy problem that I came up with, which should really not be used in real life. But let's say that you want to predict the mileage of your car or any car. And for reasons that one doesn't quite get, you've decided that the mileage of your car depends on its weight and its age. Maybe not the greatest idea, but we are not automobile engineers. We are machine learning people. So you go around collecting some data, and you have 4 data points. And you have, for example, in this particular data point, the weight of the car is 36.2 in some units, and it's 2 years old. And you measure its mileage, and you get that the mileage is 25. So what you want from this is some method for predicting the mileage of a new car well, not a new car, a new instance, could be a new car, could be a used car, who cares? Where you measure these two features, x1 and x2, and you want the value of the mileage. So from the point of view of the discussion that we've had in this class, our instances consist of two real numbers. So it's in R2. And the label, the goal of the task is to predict a label which is a real number. So you want to map a point in R2 to R. There are an infinite number of functions that can do this. And once again, we are faced with the question of how do we choose a good function? In linear regression, we make an assumption. We make an assumption that the target label, in this case, the number, the mileage, is a linear expression in the features. It's a linear function of the input features. So something like mileage is some W0 plus W1x1 plus W2x2. What I have highlighted here are the parameters of this linear model. Now, the thing that you need to keep in mind is this expression looks very much like the kind of thing that you might see for a linear classifier. You have bias plus a dot product of weights and features. The big difference is in a linear classifier, you take that number, which is bias plus dot product of features, and you compare against 0. If it's greater than 0, you say plus. If it's less than 0, you say minus. Here, there's no thresholding. You just take the number, and that's the output. And these weights are the parameters of this model, and they form a vector. So I'll be calling this the weight vector. The goal of learning in this setting is to somehow use all the training data that you have, those 4 examples that we had, and find the best possible value for W. And once training is done, for prediction, it's rather simple. When a new example comes in, you measure the value of these features, and you apply the linear transformation. So when you have x1 and x2, you just compute the value of W0 plus W1x1 plus W2x2, and that's the answer. If this phenomenon was truly linear in the underlying features, and for whatever this definition of the word best, you really found the true hypothesis, then your prediction will get you the right label. Of course, there is an assumption here. The assumption starts off at the very beginning. We are assuming that the output is a linear function of the input. This is life does not necessarily have to behave this way, but we make this simplifying assumption. A little bit of notation. Your inputs in general are not two-dimensional, but they could be d-dimensional. So you have x, which is a vector in d dimensions, and your output is a label y, which is a real number. And to get this thing started, we are operating in the supervised setting. So we assume that we have a list of examples that have labels. So we have a set data set of pairs xi, yi. Our goal is to use this data set to approximate the label as this linear function here. Y is W1 plus W2x2 plus W3x3 plus so on. Notice that I'm not multiplying W1 with x1 because I'm assuming that the first feature is the number 1. This is exactly what we did for classification, where I said that I have a bias feature. This W1 serves as your bias for this linear classifier. And instead of having an explicit bias term, I can set the value of the first feature to be 1, and you get that bias term. Really, you have d minus 1 features plus this 1 bias term. And by doing that, I can write W is simply the dot product of the weights and the features. Or Y is simply the dot product of the weights and the features. Y is W transpose X. There was a question.
That got answered about the 1, whether it was the bias term getting folded in.
It's exactly the bias term that got folded in. Yes. Now, the goal of learning is to learn the weights W. Any questions about this? One of the things that you may have seen when you see linear regression in other places is often outside of the machine learning sort of worldview, linear regression is presented as a mechanism to understand or explain data. It's a way to explain the dependencies between the target variable y and the features. We are using the same idea here, but here we are using it as a prediction rule. It's not enough if we explain the data, we would like to make predictions on future examples. Right? The goal of machine learning, as always, is still generalization. We would like to make predictions on new instances that are not in the set D, and hopefully we get the correct label. Tell me what does correct mean for regression? So you may have some examples here. Very clearly, these dots, I mean, let's say that your input is this one-dimensional vector, it's just a number, and your label is also a number. These dots are not clearly not forming a line, right? But with linear regression, you might get something like this. So you get a line that sort of passes through the middle of this data. But really, for maybe only one point, does it actually sit on, only one point sits on the line. So what does correct mean here? Yes. The minimum residual. You're using technical words here. What does that mean without using the word residual or the word minimum? So for every point, you're measuring the distance to the line, and you're trying to find the minimum, the line that minimizes that value. But you answered a question that I was going to ask next. The question that I really asked was, what does correct mean? How do you measure error here? And the answer is really what you just said, the residue. The error is for, let's say for this point here, or let me erase everything. Let's say for this point, the ground truth is this value here, but the line only predicts this much. So the error is this gap here. So it over predicts the value. And yeah, today we're going to have a lot of tech issues. I'm working on a very fragile system here. Let's hope things work. So unlike classification, where the error is defined as if the ground truth is a 1, or unlike binary classification, if the ground truth is a 1, the prediction is a 0, then it's an error, or vice versa. If the ground truth and the prediction are not equal, then you lose a point. Here, there is a more graded difference. So there's a gap that we can measure. So there's a notion that if the prediction was this, that's better than the prediction being somewhere here because the error is so much bigger. So the error is a little bit, not a little bit, the error is a real number, not rather than just this decision of whether you got it right or not. So this is for one dimension. But notice that in deciding to choose a linear classifier, or sorry, a linear regressor, I have made an assumption about the nature of the data. I could have chosen to fit a polynomial to this data. I could have chosen to fit a complicated polynomial, and if you pick a high enough degree polynomial, you're going to get something that fits any data set perfectly. And by choosing to use linear regression, what we are saying is it's possible that I can fit every point perfectly, but I'm willing to live with the error because I believe that the higher degree polynomial is not going to generalize. That's the implicit assumption that you make whenever you use any hypothesis class, including this one here. Same idea applies for higher dimensions. With 2 dimensions, you're predicting a plane. In 1 dimension, you're predicting a line. With 2 dimensions, you're predicting a plane. In higher dimensions, you're predicting a hyperplane. In classification, the hyperplane that you predict slices the space and says one side is plus and the other side is minus. In regression, the hyperplane that you predict is actually the point on the hyperplane gives you the value, the height of the hyperplane from the input subspace gives you the value that you want to predict. Questions about this hypothesis class. Just like with classification, there are other choices for regression as well. We'll be looking at linear regression because it contains all the interesting parts for regression. And then we'll talk, maybe if time permits, we'll look at how we can generalize this to nonlinear. There are a few different approaches. And eventually at the end of the semester, towards the end of the semester, I'll talk about how you can use neural networks for regression, which it turns out does not change the idea that I'm going to present today too much. The mechanics of it doesn't change, but your hypothesis class becomes richer. Questions? Otherwise, I'll keep charging ahead. No, that sounded more like a threat. I'll go ahead. So, anytime you see a new hypothesis class, you have to ask yourself the following questions. First one is, what are the assumptions that this class of functions makes? In other words, what does this class of functions represent? What can it represent? With linear classifiers, it can the class of functions was representing hyperplanes, and there were certain functions that are linearly separable. There are some that are not. With linear regression, you're essentially assuming that the output is a linear function of the inputs, which means the hypothesis is really a hyperplane. First question was, what class of functions does it represent? The second question is, how do you make predictions on new examples with this hypothesis class? Let's pretend that somebody else did the learning. How do you make predictions? With linear regression, it's very simple. A new example comes in. Example is just a set of features, right? New example comes in, you apply the linear function. We're done. The third question is, how does learning proceed? How do you actually find the best parameters in the supervised setting? I'm talking about the supervised setting because that's the easiest one, and that's the one that we are going to talk about for most of the semester. But you can generalize that later on into other kinds of settings also. But in the supervised setting, how do you find the best model, best set of parameters? So we're going to have that discussion right now. How do we train the linear classifier, or sorry, linear regressor? And for that, I'll introduce the least mean square objective. The goal of learning is, given a set of examples that have been labeled, we want to find the best weight vector. The word best, of course, is underspecified. Depending on what your eventual goal is, you could choose to operationalize best in different ways. The one that we're going to look at is perhaps the most popular version of that, which really is it naturally leads to an objective and an optimization problem. To get started, we can ask, let's say there's some input x, I, y, I in the training data. Just one example. And there's a certain weight vector, w, that we are currently entertaining. I would like to assign points to that weight vector for doing a good job. Or let's say we are pessimistic. I would like to take away points from that weight vector for doing a bad job. What does bad job mean? And that's the answer that you gave earlier. We can measure the gap between the ground truth, yi, and the prediction. A weight vector that makes this gap really large is worse than a weight vector that makes this gap really small. However, let's say that this is your weight vector, and let's say you have, well, let's start with the point first. Let's say your point in the one-dimensional example, let's say this is the labeled example. This is your x, and this is xi, and this is yi. And suppose there is one weight vector that does something like this. So the gap is this much here. There's another weight vector that goes here, and this is the gap. And the third one that goes here. And that's the gap. So let's give these names. Let's call this A, B, and C. Now notice that A and B are, so it's supposedly, I mean, let's pretend it is, on the at an equal distance on either side of the true label. It does not matter whether it's above or below, these are equally bad. C is worse than both A and B because the gap is much higher. And to make sure that A and B get the same penalty, we use the absolute value here. So the cost of making a mistake is the absolute value of the difference between the predicted label, which is W transpose X, and the ground truth Y. This is the penalty that we assign to this particular weight vector on this example. Questions about this idea? Okay, this is for one example. I can measure the cost for every single example in the training set. And I can do that by just adding up. I can just take the difference and the absolute value. I could take the absolute value, but I could also take the square. The square function also has the same behavior in that it erases the sign. It treats positive and negative deviations from the actual value equally. And square is a better function for us because we are going to take derivatives, and we know how to take derivatives of squares rather than absolute values. Well, for the most part, squares are better than absolute value for our purposes. So for each example in the training data, we have M training examples. For each example in the training data, we can measure the squared error and add it up. If we do that, we get a measure of how bad is this particular weight vector W on the data set. So this is the total cost, sometimes also called the loss, associated with this particular weight vector on the data set. If your learner chooses this particular weight vector, it is choosing to make this much squared error. Does that make sense? This is the loss or the penalty that you have to pay for settling for this weight vector W. And now that naturally leads to a learning algorithm. Sort of a little bit of fine print here. Like I said, this is the sum of all the squared costs on the training set. We have the summation is over the training data here. So this leads to a natural learning algorithm. Every single weight vector is assigned a cost because for any weight vector I choose, I can compute this value. So a learning algorithm, what it's going to do is it's going to search over the space of every weight vector and find the one weight vector that has the lowest cost. I have made a few assumptions in that previous sentence. There's a question on Zoom. I will come to that in a minute. I've made a few assumptions in that sentence. The first one is the learning algorithm is going to search over every possible weight vector. Weight vectors are real numbers, so we are going to search over an infinite space. Learning, right? The second assumption is weight vectors are searching for weight vectors gives you linear regressors, but that's not an assumption really because we are defining the linear regressor, the function, entirely in terms of the weight vector. Learning is search over functions, but equivalently learning is search over these weight vectors because the weight vectors define the function. The third assumption that I said was our goal of learning is to find the one weight vector that has the lowest cost. How do we know there's only one weight vector with the lowest cost? Maybe there are two equally good or equally bad weight vectors. We'll come to that question a little later. There is a question on Zoom. Where does the half come from? Technically speaking, you don't need the half. I could just add up the costs and you're good. The half is there only because eventually I'm going to take a derivative of this. A derivative of a square is 2 times something and the 2 cancels out. It's there so that eventually when we implement this thing, we don't have to keep track of a 2. A variant of this also involves, instead of dividing by half, you can also divide by 1 over 2m. There are m items here, and you can divide by, if you divide that by m, you get an average. rather than a sum. It doesn't really matter because m is the number m does not the weight vector w doesn't change depend on the number m. The choice of which is the best one doesn't depend on the number m. If average is low, the sum is also low. Okay, what I have written down here is called the least mean square regression, the least mean square objective. We have the error y minus w transpose x. By taking its square, I have what's called the squared error. And I'm adding all the squared errors up, and I'm getting the total squared error. Let's pretend that I'm also dividing by m here. M is the number of examples. So then I get the mean squared error. And the goal of learning is to minimize over all possible weight vectors this particular function, the mean squared error, and find the minimizer of this expression. Have people seen this expression before? Yes? Some version of this. I mean, it may not be exactly this, but something that looks like this. I hope you've seen this before. If not, that's fine. You're seeing it now. So notice that I have done something interesting. I have a learning problem. The learning problem is to search over all possible linear regressors. And instead of designing a learning algorithm for that particular task, searching over the space of all real numbers, real valued vectors, instead what I'm saying is I'm going to write down declaratively, I'm going to declaratively state this optimization problem. This optimization problem says minimize over all weights. That expression, this is in the previous slide, I call this J of W, the cost vector or the loss associated with this weight vector. So I said, I did not tell you how to solve this problem. I just said, here is the statement of the problem. I've defined the notion of a best weight vector as the one that minimizes this expression. And suddenly, I'm freed from the problem of designing learning algorithms. I don't need to create learning algorithms anymore because I make it somebody else's problem. There's an entire community of people who study mathematical optimization. Rather than me inventing learning algorithms, let me make it their problem. I'll just write down these objectives, give it to people who study mathematical optimization, and they will solve the problem for me, and my job is done. I say that, but actually they're going to be solving the problem using their tools. This is an instance, this is the first instance this semester of this idea of learning by optimization. Framing the problem of learning as a mathematical optimization problem. This is the most popular strategy for machine learning today. Almost every single successful application of machine learning that you hear about, one way or another, does exactly this. It frames an optimization problem that says, here is the cost of choosing this particular hypothesis, this particular weight vector, or these parameters, and now minimize the cost over the training data. And suddenly it becomes an optimization problem, which you can use tools from optimization, the optimization community. One of the most popular strategies for learning by optimization involves compute using the gradient of this objective function. We'll be talking about that in a bit. The gradient is simply the direction in which the function grows the fastest. Gradient descent is really this idea that if you want to minimize the function, which is what we're doing, at any point, find the direction in which the function grows fastest and go in the opposite direction. Keep doing this again and again, you'll come to the bottom. That's the loose idea. And we'll see a slightly less loose version of this very soon. That said, though, for this particular objective that's on the screen right now, you do not need to use learning by, you do not need to use gradient descent. You can literally solve this optimization problem on paper. There is an analytical solution for this. You don't need gradient descent. But this is a special case. It's like one of those few instances where there is a closed form solution. I will leave that as an exercise for you to think of the closed form solution. I'll give you a hint. The hint here is you do what you learned in, I think, Calc 1 or 2 or something, where you take the derivative and set it to 0, right? For minimizing or maximizing functions. That strategy works here. It works very nicely. You get a beautiful way of doing things. Questions? This is just one strategy, one objective function for linear regression. There may be other objectives. Maybe you don't care. Maybe you have other preferences you want to impose. Maybe you don't think both sides of the error are equally bad. Maybe the error of going above is much worse than the error of going below. In which case, you have to change this objective function and so that it penalizes certain types of mistakes more than certain other kinds of mistakes. And then you can no longer necessarily derive this analytical solution, and you have to use a gradient-based method. The gradient-based strategy is more general in that it doesn't really care about whether the objective has certain clean properties. It's it's an algorithm that just works. Almost, with some caveats, of course. So let's talk about gradient descent. Gradient descent is a general strategy for minimizing a function like j of w. Imagine that you have, in this cartoon example here, there is this w which you may have more than one dimension, but let's say that all the dimensions of w are packed in this one line here, and j of w is the vertical axis. And every point here is the cost of choosing a certain value of w as the best. And the goal is to minimize this function, which really means you want to get to the bottom of this valley, and the w that takes you there is going to be declared as the winner, as the best weight vector. And there are many different intuitions here. Gradient descent has the following general structure. You start off with some initial value of w, let's call that w naught, and it sits here. The corresponding value of j is right there. And you compute the gradient of the function j at that point. The gradient of any function at a certain point is the direction in which that function is increasing the fastest. I'll give you an intuition that especially is helpful in Utah. Imagine that you are in the mountains and you need to get to the bottom of like a valley. And let's say you're walking in the mountains and you can't see far, you're stuck in fog. You just need to look, you can only look in the immediate neighborhood around you. How do you get to the bottom of the valley? Don't try this, by the way. What I'm describing is dangerous. It's it's only for illustration. So how do you get to the bottom of the valley? The idea of gradient descent is the following. You can look in your immediate neighborhood, and let's say that the mountains are nice and smooth, unlike the real ones. You look around in your immediate neighborhood, and you feel around, and you find which direction is going up. And you assume that, yeah, if this immediate step is going up, then the mountain thing going up this way, the valley must be the other way. So you turn, do a 180, take a step in the opposite direction. You're still in the fog, you can't see around, but you may have made progress if it was actually the gradient. Now what do? You feel around again, you find the direction in which the mountain is going up the steepest, do a 180, take a step in the opposite direction. You keep doing this till it feels like there's no change. At that point, you are at the bottom. Don't try this at home or in the mountains. But that's really what gradient descent is doing. You keep iterating until convergence. In this case, the direction in which the gradient here, this is the tangent line. The gradient at w naught looks something like this. If you go in this direction, the value of the function increases. So you do a 180, you turn and you take a step in the opposite direction of the gradient. How big of a step do you take? That's a step size. That's like the R that you saw in perceptron. It's the learning rate. I can take a giant step, go from here to here, and I've actually gotten myself in a worse place. You have stepped over the bottom. I can take a tiny step, go from here to here, and that's going to make progress incredibly slow. One way or another, you have to make a call. You have to decide how big of a step you want to take, and you take that step and you end up with W1, and you repeat the process. At W1, you compute the gradient again. You see that the function increases in this direction. You take a step in the opposite direction, and you get to W2, and you get to W3. And of course, because of the weird way in which the slides are working today, this animation doesn't look nice, but you can imagine how this looks. You keep taking a step in the opposite direction of the gradient till eventually you've had enough. And had enough is mathematically, it's called convergence. You have decided that either you run out of time or you somehow come to the conclusion that you are close enough to the bottom that it doesn't matter what you do. At which point you're done. So in this case, this W3 here is maybe close enough to the bottom of this valley that you don't care about the gap anymore, and you can declare convergence. Questions? Oh, I'll get to the yes.
For lack of a better word, would perfect convergence essentially be the points where the gradient is zero?
Yes. So think back to your calculus lessons. At the point where the gradient is zero, if the derivative of j, let's write this in notation. If the derivative of j at a certain point w is zero, that means that point is a local minimum or a maximum. And so you can't change the value of the function by taking any local steps. So you're done.
What happens if we get to the point of, say, a function that has multiple local minima?
That's an excellent question. And I'll repeat the question. What happens if you have multiple local minima? Two answers to that question. The first one, it so happens that this function here has only one local minimum, has only one minimum. It's a function, it's a type of function called a convex function. There's only one minimum. And in which case you're guaranteed to get to the global minimum because there's only one minimum. Second answer, if you have more than one minimum in general, then what you have to worry about is where you start. Your initial point will decide which value you enter. And how do you know where to start? Here I said, start with an initial guess w. W naught, because this function has only one minimum, or more precisely, because this function j of w on the screen is a convex function, it does not matter what your initial guess is. But in general, if your function is not convex or has multiple minima, then your starting point will dictate where you end up. And that is definitely the case for any non-trivial hypothesis class. Pretty much every single neural network that we hear about has that property. The initial point dictates where you end up, which from an empirical point of view means you have to run your experiment multiple times with multiple starting points, multiple random seeds, and hopefully there's some stability. Yes.
So is there a way using gradient descent
with gradient descent, you'll only get to a minimum. You can't get to a maximum. If you want to get to the maximum, you do gradient ascent, but that's a minor detail. The only way you can guarantee that with gradient descent, you'll get to a global minimum is if your function is convex. Actually, let me rephrase that. If your function is convex, you're guaranteed to get to very close to the global minimum. If your function is not convex, there are no bets. Yes.
So is there any way to define the class initial point except the
For this particular objective function, it does not really matter. Also, to answer the related question on Zoom, this function is convex irrespective of what your dimensionality is and such things. And because it's convex, it does not really matter what your initial point is. The only thing that changes with respect to your initial point is how long it takes to get to the bottom. One metaphor that I've seen being used for gradient descent is imagine that you have a ball rolling down the hill. The initial point is right there, and the ball just rolls down the hill, and it settles somewhere at the bottom. And the farther you are away from the minimum, the longer it takes to get to the bottom. For a global, because there's only one global minimum, no matter where the ball starts, it's going to end up at the bottom. Whereas for a function that has multiple minima, it may look something like this. If you start here, you'll end up here. If you start here, you'll end up here. And if you start here, you can end up here. And it seems like the last one is the better one. How do you know? There's really no good answer. Because we're talking about functions that the dimensionality of these functions is the number of, the dimensionality of the W is really the number of parameters you have. And when we are training these models, the number of parameters in the largest models in existence today, the number of parameters can be high triple-digit billion, sometimes reportedly even trillion. In that high dimensional space, we have no clean way of knowing anything other than hoping that it works. Okay, let's write this to look like an algorithm. Gradient descent for the least mean square objective, where remember the objective is this function here. We are trying to minimize that expression there, which is a function of W, but also the data set. Changing the data set changes the function. So our goal is to find the best W. So you initialize your W naught, and because, as I said, this function is convex, it does not matter where you initialize it. So, pick your favorite initializer, maybe just 0. And then you keep iterating. At every step, you compute the value of the gradient of the function j of W at Wt, at the tth step. I'll call it this expression here. In case you want to know how to read this, this is the Greek letter. I think it's the Greek letter. I don't know. It's nabla. I'll just call it the gradient of j at Wt. That object there is a direction. It's a vector. The dimensionality of the gradient with respect to W is exactly the same as the dimensionality of W. So then I can subtract Wt minus the gradient of j at W. In other words, what I'm doing is I'm taking a step in the opposite direction of the gradient. The gradient points in the direction of, in a certain direction. Because I'm subtracting, it's a step in the opposite direction. You're not just subtracting, you're taking a step in the opposite direction, but you can take a small step or a large step, and the size of the step is determined by this number R, which is called the learning rate. For now, just assume that the learning rate is a small constant. We'll get into the details about how to pick learning rates and such things later on. There's a question on Zoom. I'll read it out. Just to make sure I'm understanding this correctly, even if we have a billion parameters, the function j of W is convex. So we'll always find our global minimum, but it may take more time. That's right. If we are solving this exact optimization problem, it doesn't matter what the dimensionality is, it's convex. It may take longer because you're subtracting a whole bunch of extra things. It may take longer to find the minimum, but if you have a convex function, you're guaranteed mathematically that gradient descent will take you to the minimum. It doesn't matter how many parameters there are. On the other hand, just to make things clear, the billion parameter model that I mentioned, which is basically, I was thinking of DeepSeek, which is 670 billion parameters, definitely not convex. Very, very far from convex. We have no idea whether it's convex. Well, no, we have a very good idea that it's not convex. So there are no such guarantees that we'll get to the global minimum. It's not just DeepSeek. I mean, or GPT-4, ChatGPT, all of these things are incredibly non-convex functions. When I say incredibly non-convex, what I mean is the landscape, right? In the previous picture, the landscape looks like the smooth curve. The landscape for those things might look very, very, very jagged, which means depending on where you start, you could end up in a very different place. We believe it does. We have no idea because we're talking about multiple billion dimensional spaces. I saw your hand first and then you. Yeah.
So is this loop just running, this is running till convergence?
This is running till convergence, and I haven't told you what convergence is. Basically, it could be a hyperparameter, capital T, like we talked about with the perceptron, where you say, I'm going to run this for 10,000 steps. Or it could be somehow measuring the value of this function before and after the change and saying, the change is so tiny that it's less than some epsilon, so I'm going to stop. Or it could be the relative change. It's a multiplicative rather than additive.
If we're checking it against some epsilon, that would be.
That's another hyperparameter. One way or another, we have to define our notion of convergence using some threshold. Yes, another question.
I had the same question.
Okay. So you can implement this algorithm. If you have a vector library, if you have NumPy or something, you can implement this algorithm because NumPy takes care of vector subtraction. It multiplies numbers with your vectors and all that. The only non-trivial part here is the thing in the box. How do you compute the gradient of this function j? But before that, there's a question.
My question is for this slide. So if we start at the same point, but our step size, our learning is different for two times we start.
Yes.
Will we still end up at the same point?
I'll show that. I'll illustrate that with a picture. So let me repeat the question. Suppose you have a landscape that looks like this. This is a convex function. And let's say you start here and you do 2 runs of the algorithm. One of them has a giant step size. The other one has a small step size. First of all, I asked you to assume that the step size is a constant. In practice, the step size keeps decreasing over time. That guarantees convergence. But let's say that it starts off with in one case, you start with a giant step size. In another case, you start with a small one. So if you start with a giant step size, you might end up going from here to here, and then like that. On the other hand, if you have a small step size, maybe you take a step from here to here. You take smaller steps all the way to the bottom. One way or another, you'll get to the same place, but the trajectory will be different. And now you could ask me, how do I know if I should take a small step size or a large step size? That really depends on the shape of this function. Maybe if the function is, instead of this, it looks really, really, really flat, maybe a giant step size is not bad. But if it's really, really sharp like this, maybe you don't want to keep doing this all the way down. How do I know what the shape of the function is? I have no idea. So what do? Your initial step size and how it decays is another hyperparameter. Every time there's a difficult question in these sorts of things about how do I know when to stop? How many epochs do I run my algorithm? How big of a step should I take? You're really asking questions about hyperparameters. There's another question. Can we, in this picture, it seems like I might end up bouncing around infinitely. How do I know that I'm actually going to get to the actual bottom? In fact, you will bounce around infinitely. But at some point, you will end up deciding to stop learning. With a larger step size, it's not guaranteed that you will bounce around infinitely because it really depends on the shape of this curve, of this function. Okay, so the only thing that's left here is this, the gradient of this function here. it's all good and easy to kind of show this in pictures by saying, yeah, it's the direction in which the function grows the steepest. How do you compute the gradient of J of W? Any ideas? There's an answer on Zoom. Take the derivative. 2 hands immediately went down. Same answer. So yeah, you take the derivative. The good news is that you already know how to do this. I don't know, the 4th grade or something, whenever you saw calculus. So the grade, let's kind of build this up one step at a time. I have a function j. It's a function of w. W itself is a vector. It looks something like this. It's a vector with d elements. A sort of a useful heuristic is the gradient of a function with respect to some w has the same shape as w itself. So the gradient of j also will have d elements. Why? I mean, it's almost by construction. So it's the gradient of j with respect to w is really a vector of partial derivatives. Each one of them looks something like this: the partial derivative of j with respect to some w2 or w3 or so on. It's just a list of those things. So I don't need to show you how to compute the gradient of all of them. If I show you one of them, the rest of them are exactly the same, or they behave the same way. So let's focus on the partial derivative of the objective j with respect to wj. I realize I'm using capital J and small j. That's such bad practice. But we are stuck with this notation now. There is a certain weight vector, wj, and I'm going to compute the gradient of the objective with respect to that one number. Right? Wj is a single weight it's associated with feature xj. So I want to take the derivative of this function here with respect to wj. It's a partial derivative because there are other things in this expression. We're pretending that those things are constant. This must be fairly simple. You know how to do this. There is silence, and that worries me. You know how to do this, right? Okay. Thank you for saying yes. Well, the partial derivative of a sum is simply the sum of partial derivatives. So I can move the partial derivative inside. The partial derivative of this dot product, well, the partial derivative of a square, the square is simply twice the thing times the partial derivative of y minus w transpose x. But y minus w transpose x is exactly this expression here. Or it's w1 x1 plus w2 x2 and so on. In particular, the thing that I care about is wj xj. And this is the ith example, so I have xij. And here I have so much bookkeeping. I'm doing this in such gory detail, mostly to kind of show you how this is done. In practice, this is not how we do it. We'll use a library to do this for us. So the partial derivative of this expression with respect to wj is simply xij. There's a minus sign, so it's minus xij. And the reason why we have a half is because this 2 and this 2 can get cancelled out. So we are left with an expression that looks like this. Partial derivative of j with respect to wj is simply negative sum over the entire data, y minus w transpose x times xi, or xij, sorry. For every example, we are summing over, I is running over the examples. Nothing here should be shocking. So I'm not going to spend too much time on this. If this worries you, I encourage you to go back and convince yourself that I'm not lying to you here. But it's just standard calculus. So I have a single partial derivative. This fits somewhere here, and I do this once for each of the d features, so I get a d-dimensional vector. So I have d such numbers. Together, I get a direction in which the function grows the fastest. Questions? I know it's not easy to ask questions after I just said it's very easy to, this is easy stuff. It doesn't have to be easy. This is not necessarily obvious if you have not seen it before. Yes. Each parameter, yes, yes. In practice, what we end up doing is we will write all of this using vector algebra. So it turns out we can do this a little bit more efficiently because our hardware can handle those things. But in theory, that's what we're doing. We calculate each one of these things separately. Yes.
What does xij represent compared to the vector xi?
Xij is the jth element of the vector xi.
Okay.
Xi is the ith example. The example itself is a vector and it has a jth element.
Okay.
So that's supposed, like that's what I tried to write here. xi1, xi2, and so on till xij.
Okay.
Yes. That's exactly right. This new vector is what you multiplied with r, and then you subtract from the current weights. This has an interesting interpretation because the gradient is the sum of the error times the input itself. Each input is penalized by, each feature is penalized by how much error, each weight is penalized by how much error, how much it contributes to the error. There's a neat interpretation here. There's nothing much to say about it. It's just what the math is. Going back to what we had, you compute the gradient of the example of the weight vector W, WT. Sorry, compute the gradient of the objective at WT, and then you take the gradient step. But in order to compute the gradient, you first evaluate the function at each of the training examples. First, you compute W transpose X, you evaluate the function, then you take the difference, and then you add them all. You construct the gradient vector. This is just one element of the gradient vector, and then you update your weights. Here I'm showing vector difference, not this has j elements here. This is something like that. Questions? Yes.
This is how slow it is. This is how steep the slope is.
You are shifting it. Maybe that could be one way of thinking of it. Yeah. If the slope is very, very high, you take a you may be taking a, it's not really this, okay, no, sorry, that's not right. It's not the steepness of the slope because the gradient is a direction. The gradient is a direction. So think of this two-dimensional plane and imagine that your y comes on top out of the plane. So you're sitting currently here, and let's say the function increases the fastest in that direction. Then you move in this direction. So it's really the gradient points in the direction in which the function increases the fastest. Yeah, so that's where the reason I'm not very keen on saying you're shifting by the steepness is because of R. Because R modulates how much of a step you take. So if it depends on where you are in the learning, and R keeps changing in a certain way. And so if R is really, really small, even if the steepness is very high, the step might be really small. Yes, yes. Okay, so this is the entirety of the gradient descent. For now, like I said, R is a constant, but we'll get to the details a little later. This algorithm, as I said, is guaranteed to converge to the minimum because this function is a convex function. Later on, I think when we come to support vector machines and when I talk about stochastic gradient descent in a bit more detail, I'll talk about convex functions and give you a little bit more formal introduction to that. For now, a convex function is a function that is shaped like a cup. It has a single minimum, so you get to the bottom. Okay. Now, let's talk about a variant of gradient descent, which is more practically useful, and it fixes an annoyance with gradient descent. Let's look at gradient descent once again. You're taking the summation over every single data point in order to just make one update. Imagine implementing this. You take the first example. Let's say in the first iteration, your current weights are some W. You take the first example, you find that your W transpose X is very, very, very far away from the Y. You know that your weights are lousy. You know that you're going to change the weights. Even though the weights are really bad, you now, because you have to iterate over the entire data, you have to now iterate over every example, use your really bad weight vector to compute the prediction, compute the gradient, and so on before you make an update. You knew at the very first example that these weights were bad, and yet you have to wait to iterate over the entire data set to get an update. So the question is, could you have done an incremental update right when you found that your weight vector was bad? Could you have updated your weights rather than waiting to iterate through the entire data? So to put it in a different way, the weight vector is not updated till every single example is seen and every single error is calculated, which means it seems inefficient. To make one change to the weight vector, you have to make one full pass over the training set. You make one full pass over the training set, you get one change, and then you go back, you make another pass over the training set, you make one more change. Could we make early updates? As we make a prediction of an error, we immediately update the weights rather than actually waiting to iterate over the entire data. Does that question make sense before we talk about the algorithm? This summation could be very slow. The summation could be over a massive data set. And there's no reason to do the summation, especially in the beginning stages of learning, because your weights are bad, might as well just get early updates. So this motivates what's called incremental or stochastic gradient descent. The way it works is the following. You pick a random example from your training set. Let's call it xi, yi. You pretend that this is the only example you have. You don't have that full data set. This is the only example you have. You can compute the gradient on this one example, and you take a step. Now toss that example back into the bag of examples. Pick a new example. Pretend that this is the only example you have. Write down the objective, compute the gradient, take a step, put it back in. So you take updates based on individual examples rather than the entire data set. When you use the entire data set to take your updates, we call that batch gradient descent. We use the entire batch of examples. Here, this is the simplest version of stochastic gradient descent, where we use only one example to make your update. And each time you pick a random example. Let's see if I have a version of this written down that's slightly more. Oh, there are questions on Zoom. So I think am I late for that question? I think I don't understand your question, Jared. Maybe you can elaborate on that a bit. I'll talk about the algorithm first. So stochastic gradient descent works in the following way. You initialize your weight vector to W, and learning proceeds in epochs, very much like your perceptron type algorithm. So this T here is epoch. And then you iterate over every training example. You pick an example and you say, I don't have the entire data set. I have just one example. So J of W is, you remember it was sum over yi minus W transpose xi square. But I have only one example, so I don't have the summation. I just have this one example. I can write down the objective for that one example. I can compute the gradient for that one example. It's going to be the same thing without the summation. And I can take an update for that one example. So it looks something like this. So you update the jth feature. Here I'm writing it without the vector. I'm just showing the update for the jth feature. The jth weight vector is the old value of the jth weight vector plus learning rate times the grade of this one example. And you keep doing this till you're done. Just like we saw with the perceptron algorithm here, there's usually a step where you shuffle the examples. And that tends to be important. But the big difference is compared to the previous case, where in the batch thing, this update is outside the formula. So first you accumulate the gradient over all the examples and then make an update here. Every time you compute a gradient, you make an update. So you make faster updates. You make earlier updates than you would have with batch gradient descent. So there was, let me go back to the question on Zoom. In this case, where batch gradient descent is problematic, is it because it's just one element of the gradient vector? We don't have to do it for every point multiple times. This is true for one, not just because it's one element of the gradient vector. Every single partial derivative is going to look exactly the same. For every single partial derivative, we need to sum over all the data points. So it's not just because it's one element, it's for every single partial derivative. Okay. So this particular learning strategy, I didn't know this door opened. Okay. This particular learning strategy is actually really, really old. It was developed in the neural networks literature, and it's called the Widrow-Hoff rule. You don't see that name very often these days. These days, we just say this is stochastic gradient descent for the least mean square objective, because you don't need a special name because it's a single case. It's a one of many different kinds of objectives for which you can apply the stochastic gradient descent idea. Okay. In practice, if you have to use a gradient-based optimizer, I would recommend you use stochastic gradient descent. Why? Because it turns out it can get much closer to the optimum than the batch gradient descent, much faster in terms of wall clock. Because you end up taking early steps, and that takes you into a good enough region, at which point you declare convergence. It is actually preferable, especially if your training set is really, really large. We'll talk about convergence rates and such things in the context of much later, but just empirically also it tends to be more faster with larger data set. Let's talk about the convergence a little bit though. Your learning rate R in practice needs to decrease for your for the objective to get to the bottom of that the ball. Because if the learning rate stays the same, you will end up just oscillating back and forth without actually going. Let me draw the picture more cleanly. So you may have something like this. You take a step here, and then you take a step here, and then you could end up oscillating because your steps are too large. So in practice, the learning rate needs to decrease. There are many sophisticated strategies for choosing learning rates. A good idea could simply be learning rate R is 1 over the number of epochs plus 1. So every epoch, you kind of keep making the learning rate smaller and smaller. This is a reasonable starting point. This is definitely not the best out there. There's like a whole cottage industry of algorithms for inventing learning rates, and it turns out choosing learning rates the right way can lead to much faster convergence. But for the purposes of this class and for your homeworks and such things, this is often good enough. Also, starting a good initialization point can take you to a better place because you are closer to the answer. There are fewer steps to the objective. Gradient descent and SGD are very, very simple algorithms. Yet, it turns out, nearly every single learning algorithm we'll encounter in this class, except for the ID3 algorithm actually, can be seen as an instance of gradient-based optimization, including, by the way, the perceptron algorithm. What changes is the loss function, the kinds of classification problems, what is the hypothesis space, and so on, but the actual algorithm structure remains essentially the same. Okay, I'm ending a few minutes earlier today. Quickly wrapping up linear regression, our goal is to predict a real valued function. Or our goal is to discover a real valued function. This function takes your feature and predicts a number, and we pretend that nature has chosen to use linear functions to instantiate this hidden function. And what we saw is the first instance in this class of this very general idea of framing learning as an optimization problem, where we minimize, where we define the cost of making a mistake or the cost of making a prediction, which is the penalty function or the loss. And we frame the problem of learning as search over the functions so that the total cost is minimized. We saw two algorithms for this. One was gradient descent. Another one was stochastic gradient descent. Gradient descent is a very, very old idea. I can't think of who invented it. Stochastic gradient descent has a very clear inventor. It traces back to the 1950s. Sometimes it's called the Robbins-Monroe update from 1955 or something. For the problem of least mean square regression, and in this class, in this semester, only for the problem of least mean square regression, we don't need to minimize, we don't need to use any gradient-based learning for optimizing the cost. It turns out we can solve the problem analytically by framing the problem as a matrix problem. Any questions? There's a question. Can we apply Newton's method on gradient for this? You can use Newton's method here. In fact, you can use Newton's method in general for learning, except the problem is the Newton's method requires the second order derivatives, which for anything but the simplest case becomes harder. So we are not going to use that ever. Yes.
Still a little bit confused on the distinction between normal gradient descent and stochastic gradient descent, namely with the updating of the weights part of it. So for stochastic gradient descent, are we basically having a separate iteration over epochs where you say in each epoch, now for each training example, update the weights?
Since we have a few minutes, let me write down the difference. Okay. So for this side is standard gradient descent. For epoch, first I say the gradient, I'm accumulating the gradient for x, y in the data. So the gradient for that particular example, I take the gradient for that particular example and add it to my gradient, and this gives me, this is nothing but the gradient of the entire data set, or the gradient of the weights over the entire data set, which is nothing but sum. What I have calculated is this quantity here. And then at this level, I then say W is W minus, this is your standard gradient descent. So I'll erase this part, and because I want to make this a little bit smaller. This is standard gradient descent. Let's move this to a side. In stochastic gradient descent, I do the following. compare where the update happens.
So you're moving that weights update inside that
And I'm-
interior for you.
And I'm not adding up the gradients,
You're not having it up. Okay.
which means in SGD, here this is SGD at the bottom. In SGD, for every single example, you make you make an update the minute you see an example, rather than waiting to accumulate all the gradients and then making the update.
Oh, okay.
Yes.
Right?
WT really. Let's just pretend. Let's get rid of all the subscripts. So this should be XIYI here. Yeah, there's no WI. It's the entire weight vector. It's the entire weight vector that gets updated. Yeah. Yes. Yes. Where is that's a very good question, because also the word stochastic suggests randomness. The original stochastic gradient descent does not do this. What it does is, instead of for x, y in the data, you sample x, y repeatedly. But then there are some sort of statistical issues with doing that. Instead, what we do is we actually iterate. In practice, we actually do iterate over the data. And we introduce the randomness by introducing a shuffling step here. You shuffle the data at each epoch and then iterate over the thing so that there's a randomness. The theory for stochastic gradient descent originally, as it was developed, was for the version that you just described. Okay, I'll wrap up here. I'll end with a couple of exercises. You can use gradient descent algorithms, both of them, to work on the mileage problem. And if you feel like it, you can try to prove for least mean square regression, you don't need to use gradient descent at all. The answer is this matrix expression here. You can find this on the class website. I'll leave it as an exercise for you. All right, let's stop.